Okay, good morning, everybody. Let's get started. A little bit of orientation before we dive back in. Last Thursday, I managed to record and upload the video while I was in Boston, and then Duo authentication was down, so no quiz last Thursday. I don't know how many total quizzes we do in this course. Whatever it is that we end up doing, we then just normalize it to whatever it is, 30% of your final grade. So if we miss a few quizzes here or there, not a big deal. Yeah? Okay. Today, undergraduates, you're going to dive into assignment 6, and graduate students, you are going to start in on the first of 5 differentiable assignments. So grad students, the cadence is going to be exactly as it's been so far. An assignment Tuesday morning, which is due Monday night at 11:59 p.m. as usual. Okay, so I just want to orient the graduate students a little bit about how the differentiable assignments play out. Undergrads, you will get there in 4 weeks from now. Okay, differentiable assignments are different in several ways. The first one is that you are going to be coding up the differentiable assignments in the cloud. More specifically, you will be coding it up in Google Colab. Why can I not pause this? Let's see if I can. There we go. Okay, the reason you will be coding up the differentiable assignments in the cloud in Colab is you will now not be using PyBullet, the physics engine you've been using so far. You're going to be switching over to a differentiable physics engine called Tai-Chi. Tai-Chi is bleeding edge. It's only been around for a couple of years. Surprise, surprise, it doesn't work on every platform. So to level the playing field, we're going to do everything in Colab. Some of you may find that a step up. Some of you may find it frustrating and annoying. That's the reason. You're all going to use exactly the same version of Tai-Chi running in the cloud. First difference. Okay. Second difference is the way in which the instructions are given. Instead of reading a number of text instructions in the subreddit, you're going to be following the instructions that are directly in the video. So you're going to be watching a video, and you're going to follow along with me as we code up a robotics simulation in Tai-Chi. And then once you've got a virtual robot coded up in Tai-Chi, as usual, you're going to wrap an optimization process. You're going to wrap an optimization process around that virtual robot, which is being simulated inside, in this case, a differentiable physics engine. So far, so good? Okay. Why are we doing this all over again? In this course, we're focused on evolutionary robotics, which uses an evolutionary algorithm. Evolutionary algorithms are great because they're very simple to code up, but they have a big inefficiency, which is the randomness, the random trial and error. In a differentiable simulation, or when optimizing behavior for robots in a differentiable simulation, we can get rid of the random trial and error and directly improve from one simulation to the next the behavior of our robot. How exactly does that happen? Here's a visualization of this process. Here's a random robot in the top here, operating in Diff Tai-Chi, the differentiable simulator, and running just 10 evaluations, in this case led to the behavior that you see down here. The advantage of doing things in a non-random way when we're optimizing behavior is, of course, we can run many fewer simulations. You'll see when you get to D5, when you get to the 5th one, you can run this on your phone in about 30 seconds and optimize behavior for your robot. You're not strictly running it on your phone, you're running it on Google's data centers, but you know what I mean. Okay, so we're going to talk about differentiable optimization of robot behavior in the very last lecture of the course, but I just want to give a 10,000-foot view for the grad students so you get an idea about what's going on. As you can see here, the bodies of the robots in the differentiable assignments is going to look pretty different from the three-link, 2-joint robot you've been dealing with so far, so let's stick with what we know. Let's assume we want to optimize this familiar robot in a differentiable physics engine to do what we usually do, which is optimize it to move to the right as quickly as possible. What would we normally do? We'd have an evolutionary algorithm that is evolving populations of neural network controllers. We download one inside the robot, evaluate its fitness, drop in the next one, evaluate, 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 and on and on and on. Okay. In a differentiable simulator, same thing as before. We drop some sort of neural network controller into our robot. We've got a whole bunch of weights assigned to these synapses, and then we just run the simulator as we usually would for 100 times steps, 1,000 times steps. And then at the end, we ask the differentiable physics engine to tell us how well did the robot do. Here's where things start to change. Instead of maximizing distance to the right, we're going to pick some target location to the right. We want the robot to get here, T for target location. We then give the physics engine not a fitness function, but a behavioral loss function. In machine learning, we often refer to loss and trying to minimize loss. There's some inefficiency or errors that our potential solution is exhibiting, and we want to minimize those errors or minimize loss. When we're talking about robots, we're going to try and minimize behavioral loss. In this example here, behavioral loss is how far away the robot is from the target position at the end of the simulation. So far, so good? Loss is kind of like the inverse of fitness. Usually we talk about maximizing fitness. In this case, we're talking about minimizing behavioral loss. Let's imagine we download a neural network controller onto this robot, and for whatever reason, this particular combination of synaptic weights causes the robot to go nowhere. It either stays still or jitters in place. So at the end of the simulation, this is the distance between, we'll arbitrarily choose the position of the front link. The distance between the front link and the target is this distance. So we're going to define behavioral loss as D, the final distance of the robot from the target location. If we were able to theoretically minimize behavioral loss completely, what behavior would we get? What's the theoretically optimal thing for this robot to do? D equals 0. Behavioral loss equals 0, right? We're going to try and minimize behavioral loss. Another way to think about behavioral loss is the amount of behavioral inefficiency. How badly is the robot doing at whatever we want it to do? We want to try and get behavioral inefficiency or behavioral loss down to 0. Not surprisingly, in PyBullet or DiffTaiChi, if we download a neural network controller with a random set of weights, we're probably going to get a pretty big D. It's unlikely that the robot's going to do what we want. The magic of the differentiable physics engine and the magic of backpropagation of error, which has my vote for the greatest invention we've ever come up with, is to now take this error or this loss or this D and start propagating it backwards into the brain and the body of the robot and make changes to the brain and body as we go, so that the next time we run the physics engine forward with a robot with a slightly different body and brain, we are guaranteed, thanks to the differentiable nature of the physics engine, we are guaranteed that the next time D is going to be smaller. Question?
So if we're building controllers for this,
yes.
Can we know the plant?
Can we know the plant? Yes. So plant is engineer speak for the physical structure of the robot. Is that what you mean?
If you have the function for the plant, yes.
Yep.
If you have the function for the plant, can you just design a controller that will do what you want it to do? And then it will get easier for the evolutionary algorithm to minimize?
Could we not just design the controller for the plant or for the robot from first principles? Absolutely not. If there was a way to do that, this course wouldn't exist. It's easy to do for simple problems, but as things get more complicated, like a robot running around on rough terrain, it becomes impossible to do by hand. If somebody figures out how to do that, that will completely revolutionize robotics. But for now, we cannot do so. That's why we bring in an optimization method that tries to optimize the controller for the plant or optimize the brain for the robot. Okay, other questions? Okay, so this is the tricky bit. We've run the simulation forward. We know how badly we did. We give that to the differentiable physics engine, in this case, diff tai chi, and it does all the heavy lifting for us. It does all the back propagation of error and tunes parts of the body and brain along the way to make things better the next time around. Yeah? Okay. Last thing I'm going to say about this, and then we'll move on. Last time, we talked a little bit about calculus. So this is where the calculus comes in. We have d. We know the distance, the final distance of this object from t. But where did d come from? How did we calculate d? So let's go backwards. This is d actually at lowercase, uppercase t, which is usually shorthand for the last time step of the simulation. I see that I've called the target position t. Let's call the target position p for position. D sub t is a scalar. It's a single number that we get at the end of the simulation. Where does this distance come from? Well, in order to compute this distance between this position and this position, we need to know this position. We'll just deal with 2 dimensions at the moment. We have the x and y position here. We were given the xy position of the target position. We computed d. The physics engine saw us compute d in the code. The physics engine is watching everything that's happening in the code, and it knows that this is a function of x sub t and y sub t. The position, the x and y position of this link at the end of the simulation period. It also knows where these positions came from. In a physics engine, how does the physics engine compute the new position of an object or a link at a given time step? Where does that number come from? Recall our lecture on physics engines. What's the main equation, a simple equation at the base of all physics engines? How do we compute new positions of objects at a given point in time? F equals ma. So these positions came from the acceleration at the previous time step. We're now going backwards, the acceleration of x and the acceleration of y at t minus 1. So position at time t came from the acceleration that was computed at the previous time step. If we know the position at the previous time step and the physics engine computes the acceleration at the previous time step, it can combine the position and the acceleration to get the new position. That's F equals ma. So far, so good? The physics engine is tracking all of these things. We want to minimize d sub t. It knows that d sub t is a function of x and t. So it can compute the gradient of how x sub t changes, how d sub t changes as a function of x sub t. I apologize for my terrible notation here. Calculus tells us we can compute the gradients, or we can know how, as we modify distance, how x sub t should change. The physics engine knows that we want to make d sub t smaller. How does x sub t change as we make d sub t smaller? If d sub t is getting smaller, that means this quantity is getting smaller. What's happening to x sub t as this distance is getting smaller?
It's increasing, we're moving moving to the right.
We're moving to the right. So x sub t gets bigger as this gets smaller. So this gradient is a negative number. As this gets bigger, this gets smaller. This is ultimately the slope. Yeah? The physics engine, diff tai chi, is doing all of this for us. It knows that as this gets smaller, or as we want this to get smaller, this should get bigger. So it holds on to that fact. It knows that it wants this to get bigger, and it keeps going backwards. As x sub t changes, how does d of the acceleration of x at t minus 1 change? The physics engine knows this as well. It says the user wants this to get smaller, so in order to make this smaller, this should be bigger. But this is not something we can directly change in the physics engine. This is not yet a feature of the body or brain. This is a position of an object. So the physics engine automatically, for us, propagates things backwards and says, okay, this thing should be smaller, so this thing should be smaller. How should this be changing in order to make this get smaller? Or sorry, this get larger. We want this to get smaller. It knows that this should get bigger, so it wants to make this bigger. What does it need to do to this? If we want x sub t to get bigger, what should have been the acceleration of the horizontal position of this object at the previous time step? If the acceleration of x was 0 at the previous time step, would that make x sub t bigger at the next time step? It doesn't change it at all, right? We want to change x sub t. We want this to get bigger. So what should this be? If we want to make this bigger, do we want to make a sub t minus 1 bigger or smaller?
Smaller.
Acceleration smaller or bigger? We want to push in this direction, right? We want to make x sub t bigger. So acceleration, maybe it's not clear from the coordinate system here, we should be accelerating in this direction. That'll make x sub t bigger. So we want a sub t minus 1 to also be bigger at the previous time step. I see some furrowed brows. Have I lost folks? The physics engine is working backwards and figuring out for all these variables, in order to make this last one, the one we actually care about, in order to make this one smaller, it knows that it should make this one bigger, and now it knows it should also make this one bigger. We can keep going back. You'll notice there's 2 branches. It does the same thing for y. We'll do one more. We now know, the physics engine knows that it's trying to make acceleration at the previous time step bigger. It's trying to make a bigger at t minus 1. Can we go one step back from here? Where did a come from? Somebody mentioned F equals ma already. Remember that at every time step, including t minus 1, the physics engine calculates all the forces acting on the objects. So at t minus 1, we have the physics engine has calculated all the forces, and it knows the mass of this object. So where does a t minus 1 come from? We take the forces and divide by m. It knows that a was calculated from these 2 quantities. So it keeps going backwards. It now figures out whether f should have been bigger or smaller. And it also knows whether m should have been bigger or smaller. We won't bother following it in detail anymore, but rest assured, this is what a differentiable physics engine does. It's tracking all of these things. And after it's finished going all the way back, it offers up these gradients to you, the programmer. It says, listen, this should have been bigger. This should have been smaller. This should have been bigger. This should have been bigger. This should have been smaller. This should stay about the same. Bigger, smaller, same, bigger, smaller. It gives you all of those gradients. Yeah. To review, we've done 1,000 time steps of simulating the robot, and now we've gone backwards. And we've calculated, or the physics engine has calculated all these gradients. It's then up to you as the programmer. What do you want to do with those gradients? Yeah. Let's have a look at M for a moment. This is the mass of this object. It might say, for example, if you wanted this to have been smaller, M should have been a little bit bigger. We could take that gradient as the programmers and now apply it. We could increase the mass of this object by a small amount. The physics engine assures us if we now simulate that robot a second time, we haven't changed any of the weights. We've only made one change to our robot, which is the mass of this forward object, this front block. Physics engine guarantees us that during the second simulation, d sub t is going to be smaller. This realization that you can optimize robots in a differentiable physics engine and improve non-randomly not just the brain of the robot, but the body of the robot, that realization is like 2 years old. This is a brand new discovery in robotics. Someone was asking about the plant and the controller before. We can assume the plant, but or the physical structure of the robot, we can also optimize it now. Or not we, the optimization process can tune the physical structure, make the mass distribution of the body a little bit different. Okay, this is a little deeper than I wanted to go this morning, but since we're on a roll, might as well continue. So far, so good? Everybody understand how this is going? So one way to think about this, and you'll have time to think about this as you're coding up the differentiable assignments, I want you to pay attention as you're doing it. What is the human coder responsible for, and what is the physics engine and the optimization process responsible for? As I hope you've just seen, the physics engine is responsible for simulating the robot and telling you how to change things. It's up to you to decide which of these things you want to change. Okay, I promise, last thing. The physics engine is going to tell you how to modify M. It's also going to tell you how to modify the forces that were acting on this object at t-1. What are the forces that acted on this object at t-1 and at every other time step in this physics engine? You're all experts in physics engines now. What are the forces that act on this object? Gravity and
the normal force.
The normal force because it's on the ground. Exactly, right? So there's gravity pushing this way, there's the normal force pushing this way, and there's one more set of forces that's acting on this object.
It's the motors, right?
The motors, right? So the physics engine is an auditor. It keeps going backwards. It says, I'll tell you how to change the forces. I'll tell you how to change the forces that were coming from the motor. Where are the forces coming from the motor? Where does the motor know what forces to apply? Where are those coming from? We're propagating further backwards.
Your original definition?
The original definition of when we talked about joints and forces and motors in a physics engine, where are those values coming from? The brain, exactly, right? They're coming from a motor neuron. There's a number sitting somewhere in a motor neuron that's being passed to the motor, and the motor is turning that into a force that applies to that object. So the physics engine goes further back and says the value of that motor neuron should have been greater or smaller. Where did that value came from? It came from the weight of the synapse that connected to that motor. And also, by the way, that other synapse that connects to it. It goes all the way back, and the physics engine at the end will tell you not just how to make slight changes to the body to reduce behavioral loss, it'll also tell you how to make slight changes to the brain of the robot to also make behavior slightly better. In the differentiable assignments, you're only going to be applying the gradients to the brain. You're only going to be tuning or optimizing the brain. I would encourage, especially the grad students who are going to have time to do this, see if you can obey or make use of the morphological gradients as well. The gradients that tell you how to make changes to the body along with the brain. If you successfully do that, you will be in a group of about 6 people so far who've managed to get this far. I told you that evolutionary robotics is a new field. New things are being figured out all the time. This is the current most exciting thing going on in the field, in my opinion. Okay, it's a lot to throw at you. We will review this again in 4 weeks when the undergraduates get to this point. Any questions about any of that? No? Okay. All right. So where were we? We were making our way through lecture 8 on continuous time recurrent neural networks last time because CTRNNs were used in the original minimal cognition experiments, one of the first set of experiments in the field. So we're going to review what CTRNNs are, and then hopefully we have time to get into minimal cognition today. Okay. So what is a CTRNN? As the name implies, we're going to simulate neurons in a CTRNN where the values of the neurons are going to be changing in continuous time rather than discrete time. Okay, so we're going to be plotting the values of neurons over time, and I'm going to follow their notation. I'm going to use y sub I, where y is the value of the ith neuron in the neurons that make up the CTRNN. Okay. You'll notice as we go in the red box here, I'm going to be placing terms at different places horizontally. If you're taking notes, put them in where you see them horizontally because we're going to add things as we go. We're going to build up this equation that describes CTRNNs. We ended last time by talking about the fact that if we have a CTRNN made up of n neurons, that CTRNN is going to be described by n ordinary differential equations, n ODEs. I'm not going to write out all n. We're going to just write out one, and we're going to remember that the ith subscript reminds us that this particular ODE is the ith ODE among 19 of them. If the CTRNN has 19 neurons in it, y sub I is the value, and y prime sub I tells us how the neuron changes its value over time. Okay. In a CTRNN, there are a lot of biological, neurophysiological details that have been built into CTRNNs to make them more like your actual brain. The first one is that things change continuously in this universe and in your head. So that's the first biological detail that's built into CTRNNs. The neurons change continuously over time. Okay. Second biological detail they built in is by adding minus y sub I on the right-hand side of the equation. What does it mean for an ODE here to have its state variable on the right-hand side with a negative sign? What does that tell you about the behavior of the ith neuron? You've all probably comfortably forgotten your calculus classes. Sorry, we're going to review a little bit. How do we reason about ordinary differential equations? How do we take the math and figure out the behavior from it?
I use Laplace transform.
Okay, we could get fancy and use the Laplace transform. we're going to integrate these equations in our head. We're not going to do it perfectly, but we're going to get an idea about the general behavior of these equations. In order to think about differential equations or how values change over time, we have to start by setting some value and then watch how that value changes over time, or simulate in our head how that value changes over time. So we need to set an initial value for our state variable. Let's start by setting that initial value of y sub I to 1, or plus 1. So the value of y sub I at time t0 is 1. We plug that into the right-hand side. We plug in y sub I equals 1 into the right-hand side. What do we get on the right-hand side? We get minus 1. What does it mean for y prime sub I to equal minus 1? What does that tell you about how this value is going to start changing as time moves forward? It's going to start decreasing. Let's say we pause for a moment. It's decreased to about 0.5. Let's plug in 0.5 to the right-hand side. What's going to happen at this point as we continue moving forward? yi prime equals minus 0.5 now. It's going to decrease less, right? It will approach 0 and never reach it. So we've got asymptotic behavior. Yeah? Okay, so how did we figure out this curve? I dreamed up some arbitrary number, 1, plugged that number into the right-hand side, ran it forward for a little bit, stopped, plugged in that number again in my head, ran it forward again. Not as fancy as the Laplace transform, but good enough for our purposes today. Okay, let's play this game again. Let's reset the neuron and set its initial value to minus 1. Now what happens? Take this initial value, plug it into the right-hand side of the ODE. What happens?
We're just mirroring on the negative axis.
We're mirroring what's happening because if we plug in minus 1, we get minus 1. The rate of change of y sub I equals 1. We're increasing in value. We pause at some point. Now the value is minus 0.1. Plug that into the right-hand side. Y prime equals plus 0.1. We're slowing down, and we get asymptotic behavior. Last one, let's reset the neuron, set its value, initial value to 0. Now what happens? It stays there. Okay. What biological detail of neurons are we simulating by adding this term to our ODEs? It's one of the most salient or most important features, most obvious features of neurons.
Pruning?
Not pruning. Pruning has to do with the synapses between them. We haven't even introduced any synapses yet. We'll add the synapses in a little bit. This is mimicking the behavior of a neuron.
What was the question?
The question is, for those of you that know a little bit about how neurons behave, they built in a little bit of math here to simulate something that actual neurons do. You're sitting here quietly, so you're not burning that many calories. But of all the calories you are burning right now, 20% of those calories are being burned in here. That's a hint.
Is this just resetting to 0?
It is. This neuron will reset to 0. Left to its own devices, it always decays or approaches 0.
Is it firing?
You can think of this as the amount of firing, which is what burns all the calories. Neurons left to their own devices with no input, or if they're not told to do anything, they will very quickly stop firing. Neurons are extremely lazy. You look away for a moment and they'll stop doing stuff. They try to come to rest. All of the neurons in your brain right now, firing, but a lot of them are also pretty quiet at the moment, or quiet temporarily. Makes a lot of sense. If you're one small part of a giant machine, there are 10 to the 11 of these in your body. If these things are energy hogs, they're using up a huge amount of energy. Probably good that most of the time, if they're not needed, they're quiet. So this is a very important biological detail of neurons that they've built in to this model neural network by adding this little bit of math. We're going to add some more bits of math, and each term that we add to this equation is an attempt to try and capture some biological detail. For the creators of CTRNNs, they wanted these CTRNNs to be biologically accurate as much as possible. Okay, so far so good? Okay, let's keep going. Okay, we've added another term to our ordinary differential equation now, and just a reminder that we can see the subscripts. Remember that there is a separate y and a separate tau or time constant for every neuron in the CTRNN. You may or may not have seen this before, which is adding terms to the left-hand side of an ODE. Most of you have probably seen the state variable prime sitting by itself on the left-hand side of the equation. This is just laziness on the part of the authors of this paper. We could have added tau on the right-hand side. It would just be minus y sub I divided by tau. If you mentally divide both sides of this equation by tau, you'll end up with y prime equals minus y divided by tau. Okay. What is tau? Tau is a time constant. It's called a constant because, like the weights in a neural network, this is something that we're going to try and optimize. We don't know what this constant or this parameter should be. We're going to distinguish between constants and parameters and the variables themselves. The variables themselves, in this case, are actual neurons. In this case, time constants are positive numbers. They cannot be negative. Tell me about, let's assume that tau at the moment is very low. It's very, very close to zero. Let's assume a tau sub I of 0.0001. And let's play the game we played before. Let's set the initial value of y sub I to 1. And I want you to integrate or simulate this equation in your head. How does the value of y sub I start to change over time now? It's going to change differently than it did before because we've made a difference. We've changed our description of how y sub I changes over time. Is the neuron's value going to start to decay towards zero still? I see nodding heads. We still have minus y sub I over here, so yes. What change has occurred now with tau? If you're having difficulty simulating in your head, you can divide both sides by tau. We have y prime equals minus 1 divided by this value. How is this neuron's value changing over time now?
Does it just change the starting value?
It doesn't change the starting value. We're setting this value. We're setting the value of y to 1.
The slope will be more steep. Like it'll drop off much faster.
Like this? What do folks think? Make sense? 1 divided by this very small number, close to 0, results in a very high positive value. And we've got our negative here. Minus 1 divided by this is minus some very big number. So absolutely, this starts to decay very close to 0 very quickly. Okay, let's try this again. Let's reset, set the value of y sub I to minus 1. What happens now?
Same thing, but mirrored.
Okay. Low time constants result in Woody Allen neurons. They're very neurotic. They change very quickly, they panic, and then they're quiet again. They're very, very sensitive, these neurons. Any little nudge, if you place any value in them, they start to move very quickly. Depending on this time constant, there's something else that can happen. If this value is dropping this quickly, it can actually pass 0. And if we pause at this point, what happens now?
You go back up.
Sometimes you get something like this. This is a neurotic neuron. It's all over the place. You give it a little nudge, and you get a lot of extreme behavior. Question?
Sorry, I keep coming back to controls, but if your time constant is small like that, and you know it, you know that you can put like a hole at the origin in your controller
Yep.
to ignore it, can that whole thing still apply here, or no? I mean, I guess that's also for continuous time.
So you mean the pole being the pole balancing problem, or what do you mean by the pole?
Being like the 0 in the denominator.
Oh, the 0 in the denominator. I'm sorry, I don't follow.
Never mind.
Okay. I think the point is, in some simple problems, you might be able to derive what the time constant should be for whatever behavior you want from the plant or the robot. As usual, we're dealing with a robot that's running around on uneven terrain, and that robot is being controlled by 19 neurons that are wired up. It's not obvious what this value should be. I'm making up values just so we build up an intuition for the math here. But in real-world problems, you don't know what the time constants for the neurons should be. As we're going to see in a few minutes, evolution will take over, the evolutionary algorithm, and it's going to try and find synaptic weights to get the robot to do whatever we want it to do, and it's going to try and find time constants as well. Okay, we'll get there in a minute. Let's try another example. Let's set tau sub I to a very large number. Now what happens? We set the initial value of this neuron to 1. How does that neuron behave?
It would just take forever to reach 0.
This neuron is nearly imperturbable. This is the Eeyore neuron. If you remember your Winnie the Pooh stories, Eeyore, very chill. It took a lot of prodding to get him to do anything. Yeah. Low time constants, Woody Allen neurons, you just poke them, they freak out. Very high neurons with very high time constants associated with them, they're Eeyore neurons. If you set their initial value to -1, they're not going to change very much. Not surprisingly, you have collections of Woody Allen and Eeyore neurons in your head and your spinal column as well. There are certain neurons that require a lot of pushing to change or do something else. There are other neurons that are extremely sensitive, and they will go one way or the other depending on very slight changes in their input. So the time constant, the addition of this time constant here is trying to capture that biological detail of nervous systems. Some neurons are more sensitive than others. So far, so good? Okay. We're still missing some things. We have 19 neurons, but none of them are connected up to any other neurons. So this is not going to be a very functional neural network. So let's add in, hopefully, a term that's familiar to you by now. We're going to sum up, in computing how y is going to change over time, we're going to sum up over all the n neurons in the CTRNN, all 19. So in my example here, we're going to assume that uppercase N equals 19. We're going to visit each of those 19 neurons in time, and we're going to extract the current value from that neuron. Remember that in these ODEs, we're juggling y's and y primes. Y primes are how y changes in time. Y is the current value. The current value here of y is 1. The current value of y here is 0.9. We're going to visit all of those 19 neurons and multiply them by y sub ji, which is the weight of influence of neuron j on neuron I. Here's neuron I down here. We've got another neuron out here, y sub j, another neuron, another neuron. We're summing up over all 19 neurons to compute the rate of change of the ith neuron. What does that mean? What does that tell you now about the neural architecture of this CTRNN? Remember that neural architecture is how many neurons are they, how are they arranged, and how are they wired up? How is this CTRNN wired up?
They're all connected.
They're all connected, including to themselves. CTRNNs are capable of memory if it's required. Depends on what we want the robot to do. Hopefully this is familiar. So when we compute the ODE at every time step, we're going to compute this weighted sum. We're going to add it to this. And then whatever that total value is, we're going to divide it by this. What you've seen up till now is that this sets the new value of the neuron at the new time step. In a CTRNN, that's not the case. The influence of all 19 neurons on the ith neuron, it influences how that neuron changes going forward. Let's go back to try to understand what that means visually. Let's make things simple. We're going to set the time constant to 1, which means we can forget about it. And we're going to set y sub I, we're going to set it to 1. And we're going to think now about how this neuron's value changes. It's going to try and decay down to 0 due to this term. The neuron is still lazy, but there's a counteracting force here. How do we think about this? How do we describe how the behavior of this neuron is going to change going forward? It's being influenced by all 19 neurons, including itself. How do we think about this? Can we think about this? I haven't told you what the W's are yet. Let's make things easy on ourselves. Let's assume that all 19 W's, all the incoming 19 weights to this neuron, let's assume they're all 0. Then we just go back to what we had before. The behavior of this neuron, it's trying to decay towards 0. This is 1. We're okay. Let's keep all of the W's 0, but let's set one of those 19 W's to 1. This one. So all the other 18 neurons in the CTRNN are not influencing, they're not influencing this neuron at all. This neuron is only influencing itself. What's going on? We set this value to 1. It has a time constant of 1.
So it would be 0.
We know that this is minus 1 because the current value of yi is 1. So we've got minus 1 plus 1 times 1. Minus 1 plus 1 is 0. The rate of change of this neuron is 0. Change is 0. There is no change. We get this. What's going on here? What does this mean? We have a self-connection that's at 1. The neuron is stimulating itself. It's keeping itself on. It's telling itself, don't be lazy, don't decay to zero. It keeps itself going. It's burning calories. Whether that's a good thing or not, we don't know yet. We haven't even defined any behavior. We're just trying to jump back and forth between the math and a visual interpretation of it so we can build up an intuition about what's going on. Let's leave this ODE exactly as it is. Time constant of 1. Time constant of 1, only one of the 19 weights is set to 1. And now we're going to set the value to -1, the initial value of the neuron to -1. What's going to start happening now? What's the value at the right-hand side of this equal sign? We've got initial value of -1, plug that in over here. So this term is +1 plus what's happening here?
Wouldn't it be -1?
The weight is 1. 1 times -1 gives us -1. What happens? Same thing. Nothing happens. These two terms on the right-hand side cancel each other out. It's a self-stimulating neuron. Whatever value it's at, it stays there. Yeah? Okay. Up till now, we've been only talking about one neuron within the set of 19 neurons. We've been talking about the ith neuron. Let's now think about all 19. We set all 19 to some randomly chosen value between 1 and -1. We need to set the neuron values to something. We set them to non-zero values, and then we start changing these as well. Let's set these to some random values. What starts happening now? What can you tell me now about the behavior of y sub I if we start by setting its initial value to 1?
yi is initially at 1, then if the sum of our weights is positive, we should be diverging from 0, we'd be increasing the slope.
Absolutely. So if the overall average over here is large, is positive, and more positive than this, it'll start to go up. If this sum over here is negative or less than this, everything on the right-hand side might be negative, and it'll start to do this. Which means the value of y sub I starts to change over time. But y sub I is now wired up to the other 18 neurons. So its influence on the other 18 neurons starts to change, which changes their behavior, which changes their behavior back on neuron I, and who knows what happens at this point. We have a whole bunch of neurons that are influencing each other. They're influencing how they change in time, not their current value. So far, so good? If all of the incoming stimulation from the other neurons is low at some point, if this overall term is near 0, the neuron says, thank God, I can rest. It starts to drop back towards 0. If this starts to diverge from 0, it'll start doing something. What is it going to do? It depends on the value we choose for this, and it depends on the values we choose for this. Yeah? Okay. Up till now, I've been saying we set the initial values for these neurons. Where do these values come from? I'm just kind of choosing them arbitrarily. They're coming when we drop a CTRNN inside the robot. Some of those 19 neurons, or however many neurons we have, some of those neurons are receiving values from sensors, like you've been doing in the assignments. So they get their initial values from whatever the robot sees and senses, and that starts influencing the other neurons. All those other neurons, they initially have their values set to 0. They're blind, they're not connected to the outside world, they're at 0, they like to stay near 0. But sensory information starts to flow into the CTRNN That incoming sensory stimulation starts to influence how the neurons change over time. And if this is y sub I, maybe y sub j starts doing this, and you get a very complicated dance and changes in values of the neurons over time. Yes?
How is this continuous time if you have I and J?
We have discrete neurons. We can count them. There's 19. So not continuous in the number of neurons. It's not infinite neurons. It's continuous.
Are those not time steps?
These are not time steps. The subscripts represent which neuron it is. You're right. I should have probably drawn this better. You can see it up here. The subscript,
Yeah, that makes sense.
actually it's confusing. You're right. The subscript here is time. The subscript down here is the neuron index. We should add a different subscript for time. It's just not shown here to try and keep things simple. Good point. Thank you. So far, so good? Okay, let's keep going. So again, everything here is put in here for a reason. It's here capturing a biological detail. This captures the laziness of neurons. This captures their sensitivity or lack thereof. This term captures how that neuron is influenced by other neurons. You have 10 to the 11 neurons in your head. You have 10 to the 14 synapses. Not every neuron attaches to every other neuron. In CTRNNs, they are. So actually, that's not capturing a good detail about nervous systems. Okay. Here's, again, something hopefully that's familiar to you. We've got sigma here, our activation function. The activation function you've seen so far is usually placed to the left of the summation. Usually we sum up all the values arriving at a neuron to get that raw weighted sum, and then we squash it through an activation function. Usually it looks something like this. In this case, we're putting the activation side inside the summation term, which is a little confusing. The way I want you to think about this is that when we're trying to compute this ODE and we're trying to update y sub I prime, we visit this neuron and get its value and multiply it by its weight, put it here, get this neuron's value, multiply it by its weight, add it to here, and so on, right? The most basic operation in all neural networks and machine learning. In this case, by putting the activation function inside the summation term, whatever the raw value of y sub I is, the minute it leaves that neuron, when we read it out and we're about to multiply it by its weight, we squash it first. Kind of an odd detail. This again is capturing a biological detail of nervous systems. If you take one of your 10 to the 11 neurons and you look inside the neuron, there is fantastic complexity going on all the time. A neuron is a fantastically complicated machine, but when it sends out a signal along an outgoing axon to a synapse, or it sends out a signal to another neuron, it sends out a spike of electricity. It sends out a very simplified version of whatever it's doing or thinking about. By putting the activation function inside here, the moment we take this raw value and we're about to multiply it by here, we do the same thing. We simplify it or squash it. Okay? This means that the actual values, the y sub I, the y sub j, the y sub k, the actual value of the neuron at any given time step, it's free to take any value it wants. We're not squashing it until we read it out. So far, so good? Okay. We talked about gains, I think, last time. What is this doing? We've mentioned so far that in a moment we're going to see an evolutionary algorithm evolving all the weights of the CTRNN. It's also going to evolve all the time constants, one for each neuron. It's also going to evolve all the gains. You'll notice that the gain and the tau, they have one subscript. The fact that they have one subscript reminds us that there's one gain for each neuron. There's 1 tau for each neuron. The double subscript here means that any given neuron has many outgoing weights. What does it mean for a neuron to have a gain of 0? We're going to have our evolutionary algorithm evolve taus, w's, and g's. What happens if evolution sets the gain of one of the neurons through mutation and crossover, sets the gain of that neuron to 0? What does that do to the neuron?
It inactivates it.
It inactivates it. It silences the neuron. The raw value of yj might still be very large and might be doing a lot of things internally. It's thinking about lots of different things, but every time it's asked to send a value out along its outgoing synapse, nothing goes out. We multiply its value by 0, which gives us 0. We put that through whatever activation function it is, gives us 0. This neuron never hears anything from this neuron. Somebody mentioned pruning a few minutes ago. The evolutionary algorithm, by setting the gains of some of the neurons to 0, effectively prunes those neurons out of the CTRNN. What if a different neuron in the exact same CTRNN, one has a gain of 0, the other one has a gain of 10 to the 6? Tell me about that other neuron with a large gain. What is that neuron doing?
It's very active.
It's very active. It's shouting all the time. Whatever its raw value is, it's being magnified by 10 to the 6 every time. If y sub j is a small negative number, it's now a huge negative number. If y sub j is a small positive number, when it sends out a value, it's shouting with a very loud positive value. Yeah? Again, inside your nervous system, some of your neurons are quieter than others. They send out spikes, they send out little blips of electricity, but the amplitude and the rate of those blips is very, very small. They're very quiet neurons. All things considered, they have little to no effect on your outward behavior. There are also neurons inside your nervous system that are very loud. Whenever they're activated, they're sending out as much electricity as they can, and they're trying to influence their neighbors as much as possible. Yeah? When you were much younger and you put your finger on a red-hot stove plate, you better hope that there is a loud neuron that starts shouting at the muscle fibers in your arm as quickly as possible. There are very good reasons to have very loud neurons sprinkled throughout your body and brain, and they are attached to sensors and muscles in a particular way that when you do this, they do things. There's also a good reason to have quiet neurons. Why aren't all 10 to the 11 of the neurons in your nervous system all loud?
There's a lot of stimulus that should influence our behavior.
Most of the time, and this is particularly true of humans, we're inhibiting our behavioral urges as best we can. We're not perfect at it, but a lot of the time, compared to our other primate cousins, we sit quietly most of the time. We're not fighting and fornicating and feeding and doing all the rest. We're kind of quiet and looking around. There's a lot of subtlety going on in our nervous system, which the fact that we're still here seems to be a pretty good strategy. About a long-term strategy, we'll see. Okay, so we now have lazy neurons, we have sensitive and insensitive neurons, we have neurons that are influenced by their neighbors, we have quiet neurons, we have loud neurons. Neurons, we're also going to associate with neurons theta, again, a single subscript that is going to be applied to the raw value. When this neuron is queried for an outgoing signal, we take the raw value and we add something to it. This is the bias of the neuron. We've talked about gains. We're now talking about biases. Biases can be positive and negative. What is this doing? Why is it included?
Well, I'm curious as to why the bias is being multiplied by the gain too.
Okay. Again, the easiest way to sneak up on building up an intuition about this parameter is mentally set it to 0. We've got 19 ODEs, we have 19 thetas, we set all thetas to 0, which effectively gives us this. We kind of understand what's going on here. Now, mentally set some of these 19 thetas to non-zero values. Let's assume that neuron J has a non-zero bias. Let's assume it has a bias of plus theta J. Let's assume it has a bias of +1.
Is it kind of like hard coding the function of the neuron, like whether it should be like influencing positively or negatively?
That's exactly it, right? So a bias of +1, it's always positively influencing its neighbors. Whenever we read out whatever the raw value is, we always add a 1 to it. Generally speaking, it's outputting a more excitatory signal. When we talk about neurons and synapses, we talk about excitation, trying to turn your neighbor on, or inhibition, trying to turn your neighbor off. Yeah? So a neuron with a positive bias is biased towards excitation. If the raw value of the neuron is more negative than its bias, they cancel out, but that's the general intuition. If a given neuron, let's say neuron K, has a theta of -1 or -10 or -1,000, it's biased towards inhibition. It's tending to send out a negative number. It's trying to inhibit or suppress the neighbors that it's connected to. We just talked about the fact that Homo sapiens sapiens tends to be quiet most of the time. The majority of the synapses, including the neurons, a lot of the connectivity in your nervous system is inhibitory. It's inhibiting or trying to shut off what the neighbors are doing. Most of your nervous system is inhibitory rather than excitatory. Okay, last detail, and then we're done. This particular notation is quite awkward. We've got uppercase I, subscript lowercase I. My apologies. Okay. What is this I sub I? This is the input of a sensor to a sensor neuron. We were setting the initial values of these neurons to arbitrary values to build up our intuition. Some of these 19 neurons are connected directly to sensors. If we took this 19 neuron CTRNN and dropped it into a 4-legged robot with 4 touch sensors, 4 of the 19 neurons, and it doesn't matter which ones, we arbitrarily pick them, they start to get non-zero numbers coming in through this term. The other 19 minus 4, the other 15 neurons, this value is always 0. When we introduced neural networks and connected them to robots, we talked about robots having sensor neurons, hidden neurons, and motor neurons. Some of these 19 neurons are going to be sensor neurons. They're going to receive non-zero values from sensors. The others that don't are hidden, and some of them are also going to be connected to the motors, and we're not talking about that detail yet. Okay, so we drop a CTRNN with random W's, random tau's, random g's, random thetas. We drop this into a 4-legged robot, and the 4-legged robot starts with all 4 feet on the ground. So 4 of the ODEs receive values of 1. The other 15 receive zeros at this value, at this term. We're trying to compute the value at the right-hand side of this equation for all 19 ODEs. We plug in the values of y sub j. The current values of all the neurons at the first time step, the value of all 19 neurons is 0. They're all shut off, but there's some values coming in. So 4 of these 19 neurons start to diverge away from 0. How do they diverge away from 0? It depends on their thetas, g's, and taus. So 4 of the 19 y values are now non-zero, and they start influencing the other neurons that are 0, and all the other neurons start to turn on and do whatever they're going to do. So far, so good? Okay, that's a lot of build-up. We've got 5 minutes left, so let's see these CTRNNs in action. Okay. We're going to see them in action in this particular robot here. In this experiment here, they wanted to train this robot to do something that's not very complicated. Shake the block up and down, shake the block side to side, or shake the block forward and back a few times. You'll notice in the inset panel in the top left, there's some fast blinking lights and some slow blinking lights. This robot is controlled by a CTRNN, and in some of the neurons in that CTRNN, the experimenters did not evolve tau. They set tau deliberately to turn those neurons into EOR neurons, to turn them into neurons that change their values slowly. The reds and blues that you see here, blue is positively valued neurons, red are negatively valued neurons. You can see those neurons changing their values slowly over time. These are the EOR neurons over here, and they manually set some of the time constants of the other neurons such that those neurons change their values quickly. Okay, seems like kind of an odd choice. Why did they do this? They wanted to not just teach this robot to shake the block left and right a few times, and then forward and back a few times, and then up and down a few times. They wanted the robot how to do those 3 motor primitives. Motor primitives. A motor primitive is shake left and right a few times. Another motor primitive is shake up and down a few times. A third motor primitive is shake the block forward and backwards a few times. They want the robot to learn or evolve the ability to exhibit those motor primitives and then stitch them together in different patterns. Shake left and right 3 times, then forward and back 3 times, then left and right 3 times. Go. They want this robot to learn to hierarchically organize motor primitives into more and more complicated motor sequences. When you're taught a musical instrument, you're taught motor primitives. Here's how to pluck an individual string. Those are motor primitives. Once you learn those, here's how to strum a whole bunch of those strings in parallel. There's another composition of motor primitives. Once you know how to play a chord, here's how to play a chord progression. You're hierarchically stacking simple actions, motor primitives, into more and more complex actions. Something else that our species is particularly good at. You all learned how to print 26 individual letters several years back, and you can now compose them into more and more complex hierarchical arrangements all the time. What we're going to see next time is you're going to see that the fast neurons, the Woody Allen neurons, are going to be responsible for figuring out how to do motor primitives. And the slow EOR neurons are going to be like a conductor of an orchestra. The slow neurons are going to push the fast neurons into different motor primitives. The slow ones are going to say left and right 3 times, forward and back 3 times, left and right 3 times, forward and back 3 times. That's why the experimenters deliberately set the time constants to create some EOR and some Woody Allen neurons. We'll finish this off on Thursday. You're working on assignments 6 or D1. See you on Thursday. Thank you.